So today you're going to continue to look at our forces acting on different objects. So we're going to work through that process that we had previously discussed in terms of identifying that free body diagram, breaking up any angles that we have, figuring out that the net force equations that we have in the x and y directions, and then doing your solving. So let's take a look at our first question. And so in our first question, we have a box on a surface. Generally, when we see these lines, that implies that we probably do have friction. We're being asked to write an expression that describes the acceleration of the box. So as with our other ones, we want to identify the different forces that we have acting on our object. So we'll start with a free body diagram. In our free body diagram, we have the weight of this box. It's sitting on a surface, so we have a normal force pulling it up. We have this applied force, could be tension or some other force, taking it in this vertical angle. And then because we have that rough surface, we can assume that we have some friction. We're trying to move the box this direction based off that force, so our friction is going to oppose our motion, meaning it's going to pull us backwards in this direction. Okay. In terms of my free body diagrams, I usually try to make those arrows as close to the lengths that they should be. So with that being said, if when I look, I have these forces, and I might need to adjust the length of my applied force accordingly. Once I've created my free body diagram, now I need to go in and identify if there's any forces that I need to break into component pieces. So these are all potentially on the axis, so this is the only one that I have at an angle that I need to break up. This force has a component that is taking it forward, and it has a component that is pulling it up. Okay. So my horizontal component of that force would be the force. Looking at where they placed my angle, I'm going to say that this side would be my adjacent, and anything over here would be my opposite. So adjacent, I'd be using cosine function for this component here, and opposite, I would be using a sine function for this component here. So with that idea in mind, this pink arrow that I have, my horizontal component, is F times the cosine of theta. And this orange arrow would be my opposite side, so it will be F sine theta. Okay. And so those are all the pieces that I have. In terms of our process, once I've broken them into angles, I need to start thinking about my net force equations. Okay. So in the horizontal direction, I obviously have this component, but I also have this component. Okay. And since they're in opposition, when I think about my x net force equation, I'm going to say that F cosine theta minus my frictional force is going to give me my net force. Okay. And my net force is always equal to mass times acceleration. Put a little x here just to keep track of my signs. Okay. Next up, I need an equation for my vertical component. So I have this F sine theta. I also have this normal force acting vertically, and then I have my weight acting vertically. So in the vertical direction, I have two components heading up, so those are going to be my two positive components, F sine theta and my normal force are working together, and my gravity is working in the opposite direction, so I'm going to subtract my mass and gravity, and that would give me my net force, or my mass times acceleration, in the y direction. In terms of this picture, this box, I'm assuming the acceleration is going to come this direction. It looks like it's not going to rise off of that surface, or I'd lose my normal force. So realistically, as I look here, this component is going to be 0 because we're not accelerating vertically. So since this is 0, I have no net force, meaning all of these need to balance. So the way that I would say that would be my two positive forces are going to balance my weight. Alright, on the x component, we're going to accelerate to that direction. So it's not fair for me to say that this is 0, so I am going to have a force. Okay, I am going to have an acceleration. So those are my component pieces here. Okay. So this is about as simple as I have in this moment. Alright. In the end, we're going to solve for the acceleration. So if I want the acceleration, that means I need to be able to isolate as many of these other variables as possible. Alright, let's talk about things that we have learned from our notes. Okay? So friction has a definition. Friction is defined in terms of an equation as the force that is greater than or equal to the normal force of the object times its coefficient of friction. This coefficient could be kinetic or static, depending on if we are accelerating or maintaining that constant or resting state, but that's my baseline. So when I look here, I can take this equation, I can essentially substitute in where that's at. So my normal force times mu, and then I'm going to keep all the other components. Alright. I might start to ask myself, what other factors do I know? And so other things that I know, or things that I can do to simplify this expression, is I can bring in some of this component here. Okay? Something that's common between them is the two forces and the two normal forces. And since I want the acceleration, I'm going to try to make that as simple as possible. And so what I'm going to do over here is I'm actually going to solve for n. So instead of adding f sine theta and n, I'm going to subtract that f sine theta over to the other side. And that's now my value for n. So recognizing that this is n, I can actually substitute that in over here. So I still have my f cosine theta. And now I'm subtracting this expression. I'm subtracting mg minus f sine theta. I still have that coefficient of friction, that mu, and then I'm still going to be accelerating. Alright. I can take this one step simpler, where I can I'm describing the acceleration, so I really want to get just a over here on its own. So in order to do that, I need to divide by my mass. If I do it to one side, I need to do it to the other side. So now my acceleration is going to be everything that we just stated. All over my mass from over here. And that's about as simple as I can go. Notice they didn't give me numbers this time around, so I can't plug in for a cosine, I can't plug in for a mass or what that force is. This is about as simple as I go. If they gave me the mass, the coefficient, the forces, then I could continue to take this further, but this is the furthest I can describe the expression or the equation to state that. Okay, for our next question, if the force is now applied as shown over here, so instead of pulling up, now we start pushing down and forward, would we expect the acceleration of the box to be greater than, less than, or equal to? I'm not going to have to do all this math, but I do want to kind of just clarify what that looks like in terms of a free body diagram. So we still have our normal force, and we still have our gravity. And we're still trying to push the box forwards, so friction is still going to try to oppose us backward. Okay. But now that that force is coming down or in, what's going to happen is if I was to break those into component pieces, instead of these two forces trying to help each other out to equal gravity, now this force and this piece over here are going to equal. So what this does is it actually means that my normal force has to become much larger as a result. Because my normal force becomes larger, and friction is related to that normal force. As my normal force becomes larger, my friction becomes larger. So I actually am going to probably end up extending this out beyond what I had earlier as well. And so this force, by being directed down, has actually increased my friction. Well, if I've increased my friction, what does that probably mean is going to happen to my acceleration? Am I going to accelerate greater, less than, or the same as I was before? Well, with more friction, it's going to be harder to move. Which means that my acceleration is going to be less. Alright, for our next question, we are going to calculate the acceleration of the 4 kilogram box. Yeah. And so again, we're just going to work through our process. So in looking, we have 2 boxes, so this time I'm going to draw 2 free body diagrams. This box is on a surface. You'll notice that there's not the little texture like there was in the previous question. So we can assume that there is no friction as a result. Okay. What this means, and so that's also going to help us accelerate this box. So in terms of this box that we have here, we have gravity pulling it down. We have the normal force supporting it. We have this string providing tension, and again, because it's not a rough surface, we don't have the friction coming backwards. If we did have friction, that friction would still have to be less than the tension or in order to cause it to accelerate. But because we have that smooth surface, we'll assume 0 friction. For our box over here, we have mass and gravity. We have its weight pulling it down. We do have the tension force holding it up. It's not on a surface like this one, so we don't have a normal force. All right. In terms of our vectors, or in terms of acceleration, if it's going to accelerate, gravity is going to pull it down. So this implies that my tension is less than that force of gravity. So that would be my free body diagrams for my 2. Now we need to identify our net force equation. So we've got our free body diagrams. I want to make sure that I have my subscripts, or that I've identified which parts are the same and which parts aren't. Okay. So this mass and this mass are not the same. So I'm going to put a little 1 and a 2 on here to help me remember that. Tension comes from this string, and tension comes from this string. And these are in fact the same string that are connected over a pulley. So I don't need to say 1 and 2 here, because these 2 tensions are part of the same string and therefore part of the same system, so they are the same actual forces. Alright, my next step after identifying my free body diagrams is to come up with my net force equation. So my net force equation for this one, I only have forces acting vertically, so I only need a net force in the y direction. In the y direction, I have tension pulling up. I have gravity, the weight of gravity pulling down, and it's going to pull that box down. It's going to accelerate that box downward. Now, if it's accelerating that box downward, I can assume that I have a negative force, or a negative net force, or a negative acceleration. Okay. This is one way to say it. If you don't like having all the negatives, as long as I'm consistent with my symbols, that's the important part. So I could also say that these 2 are going to be positive and that one's going to be negative. My directions in themselves don't matter, it's what they are relative to each other. So I could say that we're going to accelerate positive, and that means that my mass and gravity needs to be positive. I'm going to keep my little subscripts here, just so I don't lose track. And then my tension would be in the opposite direction, so I would subtract it. Both of these are correct statements. The key part is, do they follow each other in terms of their relative patterns? So if I say that down is negative, then when it accelerates down, it needs to be negative. If I say, and up is positive. If I say that gravity is accelerating it, making it go faster, so I want that to be positive, then over here when it accelerates faster, positive, and I can make this thing that's trying to slow it down negative. So it's more about how they are relative to each other than anything. All right. On my other side, I need a vertical y equation. And on this side, I'm not accelerating vertically. It's sitting on that surface. It's going to slide side to side, but it's not going to accelerate vertically. So I'm not going to have a net force, meaning that these two forces are going to be balanced. So my normal force going up minus my weight of gravity coming down, again, I'm going to give myself a subscript, have to equal 0. They have to balance each other. Horizontally, we are going to have an acceleration. It's going to accelerate this direction. That acceleration is going to come from the fact that we have tension pulling it forward and there is no friction pulling it backwards. Again, give myself my little subscript so I don't forget. I need it on the mass because my two masses are different. I don't need it on my tension because these two tensions are the same. Since those tensions are the same, this could be one way that I could take and combine and kind of find that commonalities between the two sides. So if I know that M1A is my tension, and I prefer fewer negatives, so I'm going to go with this one. Again, they're both the same equation. So let's solve for tension right here. Yeah. Again, your choice as to which one you solve for. Either one works just fine. Yeah. So pick your favorite. If this is a positive tension, I can go with that one being positive tension. Negative, negative, either one. Yeah. I'm betting that most of you probably started here when you looked at your picture, because tension being positive and gravity being negative. So as long as I said that that's negative as well, this is what I'm assuming most of you went with. So that's the one I'm going to jump off of. The math's going to work out with the other equation as well if you prefer. Okay. So my tension is, instead of subtracting mass and gravity, I'm going to add my mass and gravity on this side. And then I would have my negative mass and acceleration on the other side. Okay. These two tensions are the same, so I can say that this and this are equal to each other. M1A equals M2G minus M2A. Everything that we've done to this point is the physics. Free body diagrams that we use to identify our net force equations. Free body diagram, I used it to identify my net force equation. I didn't have to worry about sine and cosine in this case because it was only going horizontal, it was only going vertical. But now my difficulty comes into this idea of merging. Okay. Here I've merged those two, and this is really the last step of physics. Everything after this becomes algebra. Okay. So in algebra, our math teachers would tell us to combine like terms. Okay. M1, M2, M2, those are not like terms. Gravity does not have another term, but the acceleration does. The amount that this box pulls down is going to be the amount that this one pulls over. So my acceleration is the common term. I'm going to try to move them and get them on the same side. Okay. So instead of subtracting M2 and A, I can add it to the other side. And so now I have M1A plus M2A equals, over here it goes away, and all I'm left with on this side is M2G. Alright, math. So my next step of math and algebra would be, again, a is a common term. So this is like saying 3x and 2x, 6x and 9x. I don't know what this coefficient is yet, but I do know they both have an x. So I'm going to factor that variable, that a, that common term out. And that's going to leave me with my m1 and my m2. Together, they're going to equal m2 and g. And so to get the acceleration, I would need to divide by m1 and m2, divide by m1 and m2, and so my acceleration would be my mass and gravity divided by m1 and m2. Use parentheses when you put this in your calculator to make fewer errors. Another way to think about this is, as a system, both of the masses are going to accelerate. They're accelerating because there's a net force, because this force caused by m2 isn't balanced by the tension. So this one being pulled down is going to make both of my boxes move. So another way that I could think about this is, here's my F, my net force, and it's moving all of the mass at some acceleration. And so that's my set formula. Okay. All right, I can do my I do have numbers, so I can come in here and I can plug and solve using my mass and gravity, my 4 kilogram, and my 2 kilogram, and solve it out. I'm going to get about 3.3-ish. It's acceleration, so meters per second squared. Second part of this wants to know if the blocks were initially at rest, at what time, at time t equals 0, then what would be their speed at time equals 2 seconds. Okay? So this is actually going to tie back into kinematics, because we're going to see that stuff continue to move forward throughout the year. Okay? So in terms of kinematics, our first unit, we have an initial velocity, v0, of 0, resting. We have a change in time from 0 seconds to 2 seconds. We want that final speed, and because of our earlier math, we know the acceleration. So if I wanted to look on my formula chart and identify an equation that has these parts, I would find that I could go back to my really, really old one, or I can find it written as v equals v0 plus at. And again, I'm to a point where I've identified my variables, I've found an equation. That's physics. Now it becomes algebra. So in doing my algebra, I want that final velocity. We began at rest. We have an acceleration of 3.3 for 2 seconds. So 3.3 times 2. My initial velocity would be, or my final velocity, sorry, not initial, would be 6.6 meters per second.